Welcome back to our continuing exploration of statistical mechanics. We have been studying interacting systems, the systems that allow us to explain the natural phenomena, and though we actually model the different natural phenomena by certain approximations and certain pictures and things, which then goes into theory of become matured into a theory over the many decades and years. So, the theory we just were doing osmotic pressure, we are doing binary mixture, and which is a phenology that came from the experimental observation that you need to put a pressure to stop the flow of solvent, pure solvent to the solution, and that of course is a consequence of interaction between solute and solvent, but we did not have any experimental estimation of the magnitude of this interaction. And osmotic pressure allows us, the magnitude of the osmotic pressure allows us to do that, but how, we did not know. So, that was the theory of Macmillan and Mayer, who developed a detailed theory which is the extension of Mayer's theory of real gases and phase transition in terms of Mayer's cluster expansion that we have done in great detail, and that is why the Mayer's theory played a very important role, because it allowed us to think in terms of interaction, in terms they decomposed into 2 particle, 3 particle, 4 particle interactions. Then Macmillan and Mayer took that to theory of solutions, and then they explained that okay, this could be the expression of osmotic pressure. In the process, they derived the osmotic pressure of the ideal gas law. Then it exactly become osmotic pressure equal to RT, just pi becomes CRT, and C is the concentration of the solute, or RTX solute, mole fraction of the solute, which is just the ideal gas law. So the Macmillan and Mayer could derive the ideal gas law, just like you derive the ideal gas law from elementary statistical mechanics. Then what they did was what Mayer did, they derived a virial series, but in the process they introduced an effective interaction. Now, that immediately give you the idea that then I can, if I could really play around with that, I would be able to get an estimate of the effective interaction, very sought after quantity between 2 solid molecules from osmotic pressure, the way Lennard-Jones built his potential from second virial coefficient. But when you try to do that in the Lennard-Jones way, the second virial coefficient, he used what Mayer gave, that is B2 is the integration over the Mayer F function Fr, which is exponential minus UR by KBT minus 1. So, that is the effective interaction. So, WAR, and that I can also explain in terms, and the experimental, another verification of that is the radial distribution function, how 2 molecules A and A are connected to each other, which we get from neutron scattering. We can estimate how molecules are arranging with respect to each other. That is one, another way, another tool to get into the intermolecular correlations, how molecules are arranged with respect to each other. So, that the radial distribution function, how A in a binary mixture, A molecules are placed around A molecules, B molecules are placed around B, and A molecules are placed around B. These are the radial distribution functions or partial radial distribution function. In pure case, we call it just radial distribution function, GR. But they are dependent on intermolecular interactions. They are dependent on this effective interaction of Macmillan and Mayer, or which is fluoriparameter as we discussed. But how do you go about it? Okay, I told you, and we will show that experimentally we get an estimate of that directly through structure factor, which was first time became available after Second World War, through neutron scattering when neutron beams become available. These days complex system we also get through X-ray, solids we always got through X-ray, but present day development allows random systems also through X-ray, because X-rays have become now very intense from synchrotron. So these are more recent developments in the last 10-15 years, that high intensity X-ray and getting structure of random liquids from X-ray, but before we did only through neutron. So now we need several theories. We need to understand how do I discuss radial distribution function, which I tell you gives you a arrangement of the molecules, all the molecules around one tagged molecule, one specified molecule, one chosen molecule, and then the neutron scattering. So this is what will be the topic of today's lecture, and we will be able to do it again. It has been done in quite great detail in this book, and we probably will not do a great justification of this beautiful subject of theory of liquids, but it is done much more in this book. However, we will be able to take you through the basic understanding, the basic physics, basic phenomenology, the basic aspects of the field to give you an intuitive feeling and also certain amount of workings of the theory. Now this picture here is an interesting picture which we obtained from one of J.D. Bernal's co-worker. He was a wonderful person, Professor J.D. Bernal, and he was the first to really map the obtained structure of polymers, proteins, many of the things from X-ray. He is called the father of, could be considered one of the father of the biological crystallography. Okay. So this person J.D. Bernal is doing here is he built a structure of liquid water, and he then playing around it and seeing how does many of these things work with. But what he is famous for, this J.D. Bernal, is this following experiment, and this has the first thing of theory of liquids. He took a big jar and then he put lot of marbles, spherical marbles, and he jam packed them. Then he did something really interesting. Then he poured some sticky paint, like ink or sticky ink, and that goes inside this all pervades through. But then he could take out and see around a sphere where are the other molecules, because that is where this ink has not gone through. So he will find on the surface of the molecule there are patches like that. From that he would find out what is the arrangement of molecules around that marble. From that he found a radial distribution function. And when long later in computer simulation, hard sphere potential, radial distribution function was indeed calculated by computer simulation. It's very difficult to do these things analytically. Now we have some methods, analytical methods. It was found that the radial distribution function, the number of molecules around is GR, he found is nothing. Of course, there could be nothing inside here, 0. Then there is certain, this arrangement goes like that and like that. First peak, second peak, Bernal got it almost exactly correct. So that was one beauty of first experiments of J.D. Bernal. So J.D. Bernal is the father, rightly called the father of the theory of liquid structure. He is the one who experimentally measured by this very smart, simple experiment, the radial distribution function around Hart spheres. Okay, let go around. Now, statistical mechanics, at that time it was still at infancy, because we had started having some equations. Jerry Bernal did that thing 1935, and our beginning of the theory of liquids started in 1939 or 1940s, when the Yvon in France, Carcoud in United States, Born in Max Born in Germany, and they started putting a theory of liquids together by using the methods of statistical mechanics. It's probably not surprising that all of these things followed the pioneering work of Fowler and Guggenheim in late 20s and early 30s, and then the pioneering work of Joseph Mayer in 1937. So, this work of Fowler, Guggenheim and Mayer opened really a floodgate, and people started seeing how to do a theory of liquids in terms of the interaction potential. So, basic aim is I give you an interaction potential and you give me a structure of liquids. And what do we mean by structure of liquids? We mean the radial distribution function. We mean that water, the probability of having one molecule and another molecule, and that will go directly into the radial distribution function. We go back and forth in these things, because sometimes the structure of a book, the way it is developed, does not do a good justice to the neither the historical development nor the driving force inherent in any field. So microscopic thermodynamic properties, all these things, the statistical mechanics that we have all done with many times. Now, neutron scattering experiment gives you molecular arrangement. This is what I am saying. So, neutron scattering gives you a cross section called SK, the structure factor, that's S comes from, that gives you molecular arrangement, and molecular arrangement is nothing, molecular arrangement is nothing but GR. So, neutron structure give me GR, radial distribution function, that I am going to talk about now. Then all the thermodynamic properties can be in terms of GR, and there are lots of equations that have been derived, which are of some importance for a theory of liquids, but on a course of this kind we might not spend too much time on that, because it is, this lecture should be viewed as a stepping stone or an intermediate between a book of physical chemistry like Atkins, Castell and Moore, Gladstone. From that book, the contents into the real world of research and statistical mechanics and computer simulation. So, this is kind of connect these many things. So, you should take this course in that spirit, that we are going to give you an understanding and a motivation of what we do. Okay. So, now this is again schematic representation of interactions. We are talking that here you can see two particles interacting, then three particles interacting, but by three particle interaction I do not mean a three body interaction potential, I just mean that three particles are there. So, the interaction potential could be represented pairwise additive, sum of this interaction, this interaction and this interaction. So, now any given microscopic configuration of a given at a given time, a snapshot of a liquid is a very primitive and approximate, because everything is spheres, one component, atomic, all these things. But that captures such huge amount of phenomenology and huge amount of macroscopic phenomena, that it's really is the kind of the model, the benchmark model of statistical mechanics, that we play our theories and gain our understanding and then extend to complex system. So, basic idea is that if I can understand and describe this system, I can describe complex systems, very simple. So, these kind of interactions now are present. I know how to consider this interaction in terms of Raynaud-Jones potential. I have a basic idea of how the structures are, though I do not have the microscopic information. Now, I want to know that if I give you the density, temperature, pressure and the interaction potential, can you give me, if I give you UR, can you give me GR? If I give you interaction potential, can you give me the radial distribution function? That is the whole question, and how to get that. That is the aim of this in this lecture. Okay, let then go ahead. So the basic flowchart, again I am very much fond of flowchart, but unfortunately for you this flowchart will not be too much of a useful, but still let us go through it. That we start everything which I have not told you is called equation, is called Liouville equation, and that is the Liouville of n particle density. That means you have n particle, whole n particle distribution in position and time. This is what Boltzmann tried to do. These are n particles. An equation of motion of that is a Liouville equation by Liouville operator. We have not told you about that. That can be reduced essentially into an equation called BBGKY equation, which goes to equilibrium, is E1 Born-Green equation. Okay. Now, what we want to do, that the radial how do we talk of radial distribution functions? So, radial distribution functions, as I said, that I have these kind of molecules and I tag one molecule, and now I want to tell the liquid is homogeneous, there is no heterogeneity anywhere. When we say homogeneous, what do we mean? We mean that if I follow a local, I make a cubic grid, I make a grid, this is something what probably spending a little time, that I have this big thing and I make it into small grids, and now a grid is such that it has 10-12 molecules, that is kind of size. That means it is a 2 molecular diameter here, 2 molecular diameter here, and 2 molecular diameter in a cube, and that has, as I tell you, 10, 12 or maybe 20 molecules. If I system a grid like that, then now I can mentally, just like we constructed ensemble and ergodic hypothesis, all this stuff, we can look into it with, let us say I have a microscope and I am counting number of atoms and molecules into that grid. When I say homogeneous, I say that this grid over a time averaging, long time, has the same number of molecules of a grid of the same size. That is what homogeneous means, that they are the same. So, there is no heterogeneity, that means no permanent long term, one region has more density than the other region. So, we are talking of homogeneous system. Now, in such a homogeneous system, I now want to describe what is the probability of, I want to describe the structure, and as I have repeatedly saying, the way of getting the structure is how many molecules are there at certain distance r. So, I have a molecule here, then I say okay, I give you a distance r and I can now give a small shell around that, my picture similar to grid, and what is the probability or how many molecules will be in that grid. If I know how many molecules in the grid at a distance, centered at a distance r, I construct a shell, then I will be knowing about the molecular arrangement about my central molecule. I know how many molecules are there, and that really tells me many things. That will tell me what is the cage, around my central molecule. This is called caging or cage structure. In a liquid, because of high density, as we discussed the density of liquid, remember by introducing quantity rho star as rho sigma cube, and sigma is molecular diameter, and that is very large, is about 0.8 typically, while crystal is 1. So, the liquid is a very dense system, but it is random, but I need to know how many molecules are around my and at what distance they are. If I know that, then I will be able to calculate quantities like diffusion, I will be able to calculate quantities like viscosity and many other properties, and that will come very handy when I want to do chemical reactions, because how two reactants come close together, where are they placed, that will give me an idea of the rate of the chemical reaction, or they will give me about the solvation structure, how one dye molecule is solvated, how a reactant is solvated in water. It is very important to know that in order to know the many properties. So, what we are beginning to do is beginning to take a shot at those kind of things. So, coming back again, continuing with my picture here, this picture of how many molecules are there in a shell. This I now say, okay, number of molecules in a shell. If this volume, the volume is 4 pi, if at a distance r, then volume of that shell is 4 pi r square, and width is delta r of my shell or delta. This is the volume of the shell. So, now if I say probability of finding a molecule at R is this quantity Gr, whom I call radial distribution function, then that gives me number of molecule at a distance n. So, this is a wonderful relation, that number of molecules in a shell at a distance r, total number is volume of the shell, which is 4 pi r square delta, delta is the width of the cell, 4 pi r square delta, and Gr. Then Gr gives me the probability of finding a molecule at a distance r, and Gr is the radial distribution function, which is the central quantity of the theory of liquids. So, now how do you go about it? How do you go about to calculating the cage? Okay, we do what we have done before, we are taught to do. We write down a Hamiltonian, this is the momentum term and the total amount of potential energy, and total potential energy, this should be small u again, mu Ri. The probability of, in this case is the, so I want now the probability, what are the locations, what is the probability, where are the molecules distributed, with what momentum, complete distribution, complete equilibrium distribution of all the n particles. I don't know what I will do with it, but let me think about it. That will be P R N P, and that is very trivial, by I know it is e to the power minus beta h. So, I give you one particular configuration that my molecules, first molecule is in R1, second molecule in R2, third molecule is in R3, fourth molecule is in R4, fifth molecule is in R5, or like that n molecules in n positions, I give you that. So, I give you locations of each molecules. You can exchange them, classical systems, nothing much, nothing changes really. But given the positions, I can now calculate the interaction potential, this quantity. Now, I have the also momentum, position, all the momentum gives me kinetic energy. So, this is what actually Liouville equation does, is the time dependence of things. I am suddenly bringing Liouville equation because we had one slide on Liouville equation. We will talk of Liouville equation slightly, not much, because it is a more complex and the level which probably we are not going to take this course too. Okay. So, this is my Boltzmann distribution in a general sense with all the n molecules, and this is the partition function. Now, let me see if I do things correctly here. Then I go to configuration integral that we have done in Mayer's theory. Then this is the configuration integral with beta u. This is just kinetic energy term is taken out and kinetic energy term goes into this de Broglie wave. Then so now I can be little bit more. I have removed the, I have factored out momentum taken out because of classical system. I can take momentum taken out. Then I have this equation. It is the same thing. I am just saying probability of molecules at given positions one, two, 3, 4, 5, 6, 7 molecules. Say I give their positions with respect to a coordinate system, which can be corner of the box or any external reference systems. I know all the positions, and if I know the position of each particles, I know the interaction energy, and then this is the configuration integral. So, this is the complete PRN, PN, put whatever you want, is the complete n particle distribution. Is a complete distribution. This is all the information that we need, but it is very difficult to get. It is a hugely difficult quantity to get, and now we are going to simplify the things, because we most of the time experiments and theory and all our applications we don't need the full n particle distribution. I don't need to know where each particle is there. I need to know much reduced description. I need to know how many molecules around one molecule. That is the radial distribution function, not the complete distribution. Well, complete distribution is very good quantity, very noble quantity, but we don't need that in our theory and applications and equations that we derive. That quantity does not come. Okay. Of course, if I know that, then I know GR, but we need GR, we do not need the full thing. So, now it is defined in the following way, just as you could expect that that this is the full distribution function. So, in order to get a reduced distribution, lower dimension distribution of fewer particles, what I need to do? I need to do integrate out. I need to, okay, I don't need you. So, I need all the other, so I need smaller number. So, instead of P n n position of n particles, all the n particles of all the molecules of n particle system. So, one is the number of particles in the system, other is order of the distribution function. I do not need that. So, but however, I am continuing with classical mechanics. That means, I am saying, okay, in this huge number of particles, there I want this, this and this 1, 2, 3. Where are they? I am not yet, I am now still specifying n and. So, then I will integrate out all the other ones. I will integrate out that, I will integrate out that, I will integrate out that. So, what I will do? I will just erase these guys. I have integrated them out, or I will fill them up in our earlier in mere theory thing. So, these are the things I have integrated out all others. I have integrated out all others. I have integrated out, but I have to keep the Boltzmann factor. And then I say, okay, how many ways I can get these by reduced number of particles out of n particles, how many ways I can pick them up, then that is n factorial by n minus n factorial. Note that small n factorial not denominator, because we still have the distinguishable particles in their locations, which these locations are given by this Rn. We have not yet made that assumption that their positions can be intertwined. I am not doing that yet. Okay. Then I, of course, if I integrate over all of them, then I should get equal to 1. Okay. That 1 is missing here, but I think the probably is there in the textbook. Now, so now I want to now go to the reduced description. I want to know that I have only 1 here. If I have only 1 particle, I want to know in this case, let us consider inhomogeneous system, there is a gravitational field, external field. So, I want to know what is the probability 1 molecule here. Then what I do? As I said, I integrate over everything else. So, I integrate over all of that from 2 to n. And from here I have n factorial by n minus, because I now have small n equal to 1. So, I have n factorial by n my own factorial, that is n by n z n, but I have integrated over everything else, d2, d3, d3, all these things have been done. What do I get next? You can of course guess what you get next. So, when you do that, for a homogeneous liquid, I can anyway integrate over, because I can choose one molecule as the central molecule and everything else I can integrate over. Then I integrate over the last one. So, these dr2, dr3 with respect to the central TAC molecule. Then I integrate over the TAC molecule, that gives me a volume V. If I do that, they are the same. Then in a homogeneous liquid, I get density, single particle density is the number density. This is a trivial exercise, but important exercise that shows that I am formulating it correctly.